Thanks for the introduction. Hi, everyone. I'm Haochen Zhang from Tsinghua University. I'm excited to present our work on Mortise, an auto-tuning congestion control framework that optimizes quality of experience through network-aware parameter optimization. This is a joint work with colleagues from Tsinghua University, Bytedance, and Hong Kong University of Science and Technology. Let's start with why this work matters. Quality of experience, QoE, is an application layer metric used to describe users' experience. For example, in video streaming applications, the stall ratio is a pivotal QoE metric that indicates how often users encounter stalls. QoE is absolutely critical for content providers today. As we can see from this timeline, internet applications have evolved dramatically over the past 3 decades, from simple email and web browsing to today's high-demanding applications like cloud gaming and metaverse experience. With more and more emerging applications, the experience, or we say the performance, directly impacts user retention and economic outcomes. Besides application layer mechanisms, such as ABR or CDN selection, recent studies have shown that congestion control algorithms play a pivotal role in shaping user experience. CCAs fundamentally shape user experience by managing the trade-off between key transport layer quality of service metrics, throughput, latency, and packet loss. This brings us to the critical question: how do we balance these competing transport layer QoS metrics to maximize application layer QoE? Here's a scenario we see all the time. A video conferencing application needs low latency, so the operator thinks, I need a low latency CCA. They might choose GCC, NADA, or COPA. But which one is actually better for their specific situation? Operators today can only make intuitive choices based on their expertise, without a quantitative guidance. So our first key observation is that all CCAs face an inevitable trade-off between QoS metrics. In theory, there is clean rocks point, perfect bandwidth utilization with empty queues and zero loss. Showing on the throughput and delay trade-off plot, the clean rocks point will gain both maximum throughput and minimum delay. However, this is practically impossible, first due to unpredictable network fluctuations. For example, after time t, it is impossible to know whether the available bandwidth will increase or decrease. And also, there's inevitable control loop delay. The congestion signal will be sent to the server at least after 1 RTT. So to adapt to bandwidth changes, CCAs have to actively probe the network state by adjusting their sending rate. However, probing is inherently uncertain. Increasing the sending rate might reveal unused bandwidth, or it could simply lead to increased queuing delay. For example, aggressive CCAs will aim for the upper bound of bandwidth, maintaining a buffer to get higher throughput, but also have higher delay. While conservative methods will go for the lower bound of bandwidth, trying to maintain an empty queue to get lower delay. However, they will also obtain a lower throughput. Therefore, in reality, we operate on a Pareto frontier, where each CCA operates at a different operating point along this trade-off spectrum, depending on how aggressive or conservative it probes or reacts, which is decided by their internal strategy, mostly the parameters. Our second observation is that during a session, what applications prefer changes with network conditions. Traditional understanding holds that QoE preferences only vary across applications. For example, in the common case we mentioned before, video streaming always favors low latency. However, we recognize that QoE can also change within a session as the network condition evolves. So in high bandwidth scenarios, as we can see from this bitrate quality curve at right side, the quality gains from seeking higher bit rates are marginal. Thus, the application would prioritize latency for reducing stall ratio over video quality improvements to achieve better experience. But in low bandwidth scenarios, as we can see, even small throughput improvement can significantly boost the video quality. So application would prefer this even at the cost of slightly higher stall ratio. So the key point here is that the optimal trade-off among QoS metrics and thus the optimal operating point is inherently network dependent. Our third observation comes from real-world measurement. Network conditions change substantially and frequently within a session, varying on timescales of tens of seconds. These changes are both significant and unpredictable, as shown in this trace. This means real-time and continuous identification and achievement of optimal operating points are absolutely necessary. So this leads to our key insight. CCA must adapt their parameter configuration in real time to track the optimal operating point as the network state evolves. So why do current solutions fail? Some methods rely on heuristic and static configurations. They do not model the complex relationship between parameters and QoE, only use empirically tuned parameters that remain fixed throughout a session without runtime guidance, so that they cannot maintain optimal QoE under dynamic conditions. For example, the figure below shows two different COPA variants. One conservative aims for low latency, and the other aggressive, desire high throughput. While conservative method can maintain low latency, it tends to underutilize the available bandwidth and obtain lower throughput. Conversely, the aggressive method could make fuller use of the available bandwidth, but may suffer from longer queuing delays. Both methods cannot consistently maintain optimal QoE under evolving network states. Current solutions also have limited flexibility and poor adaptability. Transfer learning approaches might seem intuitive, but require minutes to hours to adapt, while CCA selection methods are limited to just a few discrete operating points. Now, achieving this dynamic adaptation is really challenging. Here's modeling complexity in relationship between parameters, network state, and QoE. Exhaustive search is computational prohibitive in production, and existing approaches lack quantitative interpretable models to predict how parameter adjustment affect QoE. We also face a metric mismatch. CCA is optimized for QoS, while QoE depends on application-level semantics. And there's also feedback latency. QoE metrics typically only become available upon session completion, making real-time control difficult. This is where Mortise comes in. We build on rule-based CCAs with explicit network models because they offer higher computational efficiency and can achieve Pareto optimal performance competitively, as illustrated as the blue dashed dot curve in the figure. Most importantly, they enable flexible and frequent parameter tuning for arbitrary trade-offs. As shown in this plot, COPA can navigate the trade-off curve to find optimal points under different network conditions. The key innovation in Mortise is introducing the QoS trade-off as a proxy. Instead of directly mapping QoE to CCA parameters, we decompose this complex problem into two tractable tasks. The optimal trade-off and optimal operating point are mutually transformed. When we achieve the right QoS trade-off, we naturally arrive at the QoE optimal operating point. The trade-off can be intuitively viewed as the slope of the tangent line on the curve. For example, if we settled at the yellow point, the QoS trade-off would tell us that we can move towards the right point for larger QoE gain from throughput than QoE penalty from delay. So our design addressed two main challenges. First, how to extract the trade-off preferred by QoE under current conditions. And second, how to identify the CCA parameter configuration to achieve that preferred trade-off. Let me walk you through how Mortise solved these challenges. So at the connection initialization, the application will provide its QoE model. Our application preference extractor aims to extract the preferred QoS trade-off in real time from this model. We start with these explicit QoE models, which consist of several metrics, MI. For example, in video streaming, video quality and stall ratio are included in the model, each associated with throughput, delay, and loss. We then translate these metrics into a corresponding QoS form, presented as a function of throughput, delay, and loss with different weights. These weights implicitly capture how strongly throughput delay and loss respectively influence the user's quality of experience. And then we will solve the gradient to extract preference hint. This hint, lambda for delay throughput trade-off and beta for loss throughput trade-off, guide our parameter adjustments. For example, lambda means how much delay we can tolerate for 1 unit of throughput gain. The second part, the trade-off controller handles the cross-dependency between parameters and preferred QoS trade-offs. The cross-dependency is highly challenging to handle in practice. Changing parameters would move to new operating points, providing different performance, which in turn may yield different QoS trade-off preference. Then the new trade-off will guide our adjustment on CCA parameters. The goal of the trade-off controller is to, through such iterative cycles, gradually converge to the optimal operating point. However, in practice, the measurement noise cannot be avoided. We need longer time to measure a more accurate trade-off. But fortunately, it doesn't require extremely accurate measurement of trade-off at all time. Our insights here are, at start, we just need to get closer to the optimal operating point. So a rough directional guidance is enough. When we get closer, we are able to get a more accurate measurement result by accumulated historical data and longer observation window to make finer adjustment in order not to overtune the parameters. So we measure the trade-off at the current operating point using an adaptive measurement period, then applies balancing feedback control to move the current trade-off towards the extracted preferred hint. The controller adjusts parameters iteratively until convergence, as illustrated in this diagram, showing the progression from current to optimal operating point. Here's a real demo showing Mortise in action. When the capacity increases at 20 seconds, you can see how delta, our control parameter, adjusts. The extracted preference lambda rises as the application prioritizes lower latency and higher bandwidth. However, the current delta value remains high, leaving the achieved trade-off to be higher than preferred. So within just 2 rounds of adjustment, less than 1 second, Mortise converges to near optimal performance, closely matching the Oracle's QoE. We've implemented Mortise on Linux TCP with eBPF, building on COPA by adjusting its delta parameters. The system has remarkably low overhead. We conducted real-world A/B testing in both wireless and wired scenarios at Bytedance. Our experiments covered 128 cities worldwide over 3 more months, with 2 real applications, file downloading and video streaming. We compared our method with 12 other CCAs from 4 different types. The result shows dramatic QoE improvement. Mortise improved both individual application-level metrics and overall QoE. We achieved great QoE improvement on both file downloading and video streaming applications. This box plot shows how Mortise consistently outperforms all baselines across different scenarios, optimizing the balance between throughput delay and loss for each application's need. You can find more detailed results in our paper. So to conclude, the optimal CCA configuration is network-dependent and time-varying. Heuristic and static parameter configuration are fundamentally insufficient. Fine-grained continuous parameter adaptation is essential for optimal QoE in fluctuating ones. Mortise addressed this by continuously and quantitatively adjusting CCA parameters to maintain QoE optimal operating points as network state evolves. Thanks you for listening. Our code is open source on GitHub. I'm happy to take any questions.